Module 4 binary tree and other trees for the subject data structure using C++. Uh, we define here the way trees are used, why tree we are using, binary trees then, the definition of tree, the definition of binary trees, and is it a data structure, linear data structure, or is it a non-linear data structure. Then we do have properties of binary tree to be discussed, four properties for binary tree, and the representation of binary tree using array representation as well as linked representation. Then we do have a common binary tree operations like finding an element using a binary tree approach, searching for a binary tree. It's an abstract data type for a binary tree we will discuss. Some of the common operations which we will be using: insert, search, delete a node from a tree, that needs to be discussed. And finally, we look at various traversal method indeed used in abstract data type of a binary tree. Some of the traversal method includes in order, pre-order method, post-order method, and even level order method. Finally, we have the ADT of a binary tree, class binary tree. So that's there. These are the topics which we'll discuss. So we will begin with, so when we talk about the tree, literally this is a pictorial diagram from nature's point of view. We have over here a leaf, we have a branch, and we do have a root. When we take computer scientist perspective or point of view, we have to turn this figure upside down so that we get this as the structure and newly adapted structure. In this, the root will be located at the uppermost position or topmost position, followed by the branches and the leaves will never be changed. But we do have one more terminology coming into play, which happens to be a node, which we can call it as an intersection between two branches. We can call it as a node. So this node would be a space wherein we fill up the elements with. That's what we have. The tree, this is the tree which we will be looking at: the root, branches, leaves, nodes. Let us discuss all this topology or terminologies later. So as we know, trees are nothing but non-linear data structure. So far we have come across various linear data structures involving stacks, queue. To some extent, dictionary can also be called as a linear data structure, whereas tree is literally a non-linear data structure. So the reason why we use linear data structure is to represent some of the real life scenarios. Like for example, you have days of a week to be represented, months in a year, students in a particular class. If you want to address that concept, then we could make use of a linear list. Either a stack you can use, or you can even use queue, and the data of this scenarios could be loaded based on this data structure. Suppose if we adapt trees, when would we look for trees? Trees we can possibly think as if for a institute like a college, we do have a management as the highest will be given the maximum responsibility, followed by the principal, followed by the departmental heads, followed by the faculties, and followed by students. That's the hierarchy which we follow in our institute. For the corporate sector, this would be the reasonably topology which they follow: president followed with vice presidents, manager, then under manager you will be having a team manager, and under team manager you might have a team lead, then you may have a team member. That way the hierarchy goes. So whenever you've been given with a hierarchical structure, then tree is a best possible data structure which you can afford to use to represent the data. One more concept which is given as an example over here happens to be the text processor, or you can think as if it's a notepad. While designing a notepad application, we figure out there are many submodules which we need to design. Notepad would be at the top of the hierarchy. The submodules of this text processor or word processor or even notepad would be files, fonts, import, cursor. Those would be the operations, the sub operations or submodules. Under each of this submodule this can also be expanded, and they may have different options. For example, you can consider this example uh, document which we are having. You cannot figure out. There are various operations over here: home, insert, design, animation, slide slow, review. These are some of the sub modules for your PPT, PowerPoint processor. So this home, this insert, design tabs do have additional operations. So overall, the complex PowerPoint is achieved with the help, or it is designed with the help of various submodules indeed, and those submodules should also be connected together to achieve a huge application like PowerPoint. So that's the reason why we use the non-linear data structure. That's for designing a complex application, wherein that complex application will be broken up into smaller application, and we design individually. So this is a more convenient example of a tree. So this is the descendants of a Joe. Joe happens to be the root. You call it as a root for this uh, tree structure, and this guy is having three children, namely Anne, Mary, and John. Mary in turn is having two children, Mark and Sue, and John is having one children named Chris. Anne is not having any children. So if the node which we have here, Joe, Anne, Mary, John, Mark, Sue, and Chris, we call those are the elements, or we call it as a node. So if there are no children for a particular node, we call it as a terminal node, or we call this as a leaf node. So in this figure, we have a leaf node as Anne, Mark, Sue, and Chris, because they don't have children. And the parent node happens to be a Joe. And the terminologies other than this we will discuss in the forthcoming slides, wherein we can discuss about the terminologies like grandparent, parent, sibling, cousins if required. So we will discuss that even. So for here in this case, if I ask you, do you have a cousin? Yeah, Ms. Mark and Chris are cousins. Fine. Similarly, for the text processor, as we discussed previously, so this is the module hierarchy of a text processor. So main problem statement is text processor. It has been subdivided into different modules. So modular hierarchy we are following here. So files we have fonts, import, cursor. So under files we do have different options like opening a file, creating a new file, saving a file, printing a file, and quitting, coming back to the main text processor. Similarly, on the fonts you can have various operations like increasing the font size, decreasing the font size, uppercase, color change. Those could be used. So here import could be possibly if you want to import kind of a figure, video clips onto this text processor, that could also be done by having many options. Cursor, various cursors if you want to insert onto the text, that could also be considered here. Or else the text operation like for the short key for left arrow mark, the short key for right arrow mark, up arrow mark. So that those can also be addressed in this cursor. So without using mouse, if you want to change the cursor position using short keys, then you can have that too. This is an example. So these two are simple tree. Now let's discuss, by knowing all this information, let's define what is the definition of a tree. Now we define a a tree. T happens to be a tree, is defined as a finite set of nodes. So remember, it should have at least one node. Then only you can define it as a tree. So it is a finite set of nodes wherein you have one node named as root. You have one node named as root. The other nodes are partitioned. So you can see there are remaining nodes other than this. They are partitioned into three disjoints. Over here it says in general you have other nodes being partitioned into t disjoint sets. So disjoint sets in the sense the elements in that particular node are different. So when we look at this figure 1, so this is having a node root, followed by that we have three partitions. So t value is 3 here, so this tree is having 3 subtrees. This is the first subtree, this is the second subtree, and this is your third subtree. Each of these subtrees are disjoint sets. Disjoint sets, the elements present in this subtree is B, E, F, and elements what you have in this subtree is C, G, I, and the elements in this subtree is D, H. So all are not common, they are different. So that's the rule what we need to look at for a tree. So it can have n number of subtrees. You don't have any restrictions for the total number of children which you can have for a particular parent. So over here, A is having 3 children, B is having 2 children, C is having 1 children, D is having 1 children. Similarly, G is having 1 children. So this is how we discuss. Now the definition of leaf already we have discussed. In this figure, how many leaves are there? We can figure out. So H is a leaf, I is a leaf, F is a leaf, and E is a leaf. So if we know the definition of leaf, leaf will not be having any children's. Leaf node or node which doesn't have any children, you call it as a leaf node, or also it is termed as a terminal node. Also we can say that if the degree of the node is 0, then also it becomes a leaf node. Fine. So now we will discuss some other terminologies in a tree. That is parent, grandparent, siblings, ancestors, and descendants. So what is a parent? Parent for BCD, for a BCD, its parent is A. Okay. Similarly for EFGH, for the nodes EFGH, its grandparent is A. For I, its great grandparent is A. So probably you are familiar with this terms. You have used it in common English, so I don't think so you'll find it difficult. I repeat, A, B, C, D are the children of A, so you call A as a parent of B, C, D. Similarly, the parent of E, F is B, the parent of G is C, the parent of H is D. And with respect to A, we can call E, F, G, H as the as the grandchildren of A, or can also be called as this A could be called as a grandparent for E, F, G, H. Similarly, A could be called as great grandparent for I. Fine. So the ancestors, what is ancestor? Ancestor for E, F, G, H are A. Could also be B, C, D. And we can say ancestor for G are A, literally the first ancestor, then you have C, so on. And similarly, ancestor is something like parent, grandparent, great grandparent. They are known as ancestors. Descendants are all things. So A, all other components other than A, all nodes other than A are all descendants of A. So that's the definition of descendants. Previously we had seen an example. This almost all components other than Joe, we told it to be a descendants of Joe. So those are inherited from Joe. So you call it as descendants, call it as derivatives. This is a base through which we get all this. So all are descendants of A. Fine. So hope all these terminologies are clear. Similarly, if we can call E and F as siblings. We can call E and F as siblings, and we can call F and G as cousins. Also, we can call F and H as cousins. Okay, but I doesn't have any cousin. Fine. So literally, the relationship between F and I. So nephew, literally we call I to be a nephew of A. Also it is a nephew of H. We will not be using this term, but that's correct terminologies to be used in tree. The next concept which we will discuss is the number of levels. So when the root will be located at level 1 always, for the levels of a tree, root will be located at level 1. Then following that, second level components, you have 3 here. For level 3 you have 4 elements, and for level you have 4, you have 1 element. So this you define it as a level of a tree. So altogether you have 4 levels here for this tree. Now we will discuss number of levels are those. So based on the number of levels, we can determine either the height or depth of a tree. Example, this scenario, we have 4 levels, so now total number of levels are 4. So indeed the height of this tree or the depth of this tree is 4. So that's how you define the height or depth of a tree. So total number of levels, which happens to be 4 in this case. So level number of levels is equal to height or depth. Next we have node degree. So remember, for each of the node, we have addressed here how many children the particular node is having. So A is having 3 children, B is having 2 children, E and F doesn't have children, and G is having 1 children, I is having no children, H is having no children. Similarly, C and D are having 1 children each. So we call degree of node degree as total number of children. So the degree of A is 3, the degree of B is 2, the degree of C is 1. So hope you can follow it using this. Similarly, this is a degree for a particular node. Now if I call what is the degree for this tree, so we define the tree degree as the maximum node degree. So when you look at this structure, which node is having maximum number of childrens, that's the maximum node degree we need to determine. So A is having maximum number of children, so the degree of the tree is 3. So the tree degree is 3 in this case. Suppose if B was having 4 children, if this was having 4, then we would have called the degree of the tree would have been 4 in that case. In this scenario, the degree of the tree is 3. That's what we have. Finally, we'll discuss binary tree now. Knowing tree, what is binary tree and what is the difference between a binary tree and a tree. Now remember one thing which we have addressed, tree happens to have a finite set of elements. It should have a finite collection of elements, whereas a binary tree, if it's defined by T, then it could also be empty. This is one primary difference. The binary tree could also be empty, but tree cannot be empty. So this could be empty, or if suppose if it's not empty, then it will be having a root element. That's correct. But remember one thing, the subtrees of the root will have a degree. The degree of the tree, the degree of the root should be at the most 2. Similarly, even the subtrees of that root, if it's having, then its degree will also be at the most 2, which means it can be 0, it can be a terminal node, it can have even 1 node, it can have 1 child, it can also have 2 child, but it cannot have more than 2 child. Hence we call it as a binary tree. So that is the definition of a binary tree. So for a tree, the difference is all node, the degree of each node could be different. It could have n degrees, whereas here at the most it can be 2. 1 is valid, 2 is valid, 0 is also valid, but it cannot be 3. So hence this is how we differentiate a binary tree and a tree. I hope this is clear. So you can think the binary tree is not empty, it has a root, and the remaining elements are partitioned into 2 binary trees, 2 subtrees. So remaining elements will be having 2 binary trees, or which 2 subtrees we will be having at least. So which we call it as a left and right subtree of a tree. Okay, so the partitioned elements, partitioned tree, we call it as a left subtree and right subtree. There is a method to transform a tree into a binary tree, and that transform technique we call it as left child right sibling representation. This is one method used for converting a given tree into a binary tree. So we will discuss that. Before that, let's look at few differences between a binary tree and a tree. So as defined, each element in a binary tree, the element in a binary tree has 2 subtrees. One or both of these subtrees may be empty. So for a binary tree, the definition itself had it could be empty, but it will be having exactly 2 subtrees. It's not exactly two subtrees is not mandatory. At least tree has at least two subtree. Okay, at most two subtrees. That's a better word. You can remove this exactly and you can change it by at most two subtrees. Each element in a tree can have any number of subtrees. So here it should be at most two, but here you can have any number of subtrees. And subtrees of each element in a binary tree is ordered. So there is a method which we call we have a binary search tree. In that case we will come to know what is this ordered binary tree and unordered binary tree. So binary tree will be always order. What is order? So in ordered binary tree, all elements, for example, if we take an example of this a b c d structure, so this is a tree, sorry, so I'll just take a binary tree example itself. So this is a binary tree. So here, rather than this, I'll just take one simple example wherein rather than expression, I'll take the numbers. Let's assume you have a number something like 10, 5 and 20. I repeat, 10, 5, 20. So you have ordering. What is ordering? So in this case, if you have 10 here and 5 here and 20 here, the node is having element value of the root is higher than left subtree, but it is lower than right subtree. So this is the formal definition of binary subtree. So they are based on some criteria. Based on some criteria, the elements are ordered. So here if you are having 10 and here you are having 5 and here you are having 20. So 10 is greater than 5 and 10 is lower than 20. So we can define the node value will be always greater than left child, but it will be lower than right child. That's binary search tree. So it is ordered. So that's the definition of ordered tree. So whereas for tree it is unordered. You don't have any rules or regulations set on the particular tree. Hence it is unordered. So this is the difference between ordered and unordered tree. Fine. Now let's look at what is this left child right sibling representation. So this is one example of a tree given. Let's see how you get a binary tree from this tree. So we are using the topology left child right sibling. So if I take this as the figure, so A is your parent, so they have 3 children and we call B as a left child, and the right sibling for A is C and D. So sibling of B are C and D, both are right sibling. Okay, and C has again right sibling, that is D. So hope this is very much convenient for you to understand what is left child and right sibling. So what we do is we scan to get a binary tree structure something like this. Then it has been redesigned, restructured, and we get this binary tree. Now first we scan from top to bottom. So first level we have one element. First level we have one element, which is your root. So you don't have a problem to deal with. So address that root. Root is address, so you get A. Then we will look at the second level. Second level we have 3 components based on A. What is its left child we need to look at. So the left child of A is B, so it has to be addressed. Same position, the left child is addressed in this position itself. So B is a left child of A. So we get the structure first. Then after that, see the right sibling. The right sibling of B we need to address. Then the right sibling of B we come across it as C. Okay, so we are in C now. Then again, what is its latest right sibling we need to figure out. So what is the latest right sibling of C? So it is D. So we get B, C and D. So this is the arrow mark now we have given. I repeat, A is the node. They have 3 children's left sibling. First they get the left sibling of A, so we get B. After that denote its right sibling. The right sibling of B is C and the right sibling of C is D. So we get this notation. So hope this structure is clear. So we are in level 2 now. Now we check, do you have any right and left sibling for B. So in level 3, we definitely can observe that B is having left child and right sibling. So we address that. B is having a left child, so it is marked here E, and E is having a right sibling, so we mark E and F. So we get this structure and we stop it at this iteration, because this structure, all elements are covered up. Now let's move on to the C. C is having one child, so we will mark it, we will note it as one itself. It's not having any sibling. Okay, so only one children it is having, so we will mark it as G here. Then similarly we will continue with this itself. So again we can figure out G doesn't have any sibling, one child, so we will mark it like this. Okay, whereas for D also, D, though this is the position now, this doesn't have any two children, so only one children, so this is also marked in this case. So if you are having one children, so you have to consider it as a left child while plotting the binary tree. If you are having two children, then you can mark it as a left child and a right child. If not, only one children, make a note, you can use a left child always. Okay, now we will reconstruct this structure. So A was your main node. Okay, it's a left child, we addressed, it was B. Then we can figure out the right, this is actually the right sibling, so the where it goes to the right child. So right child of B becomes C now, that's a sibling. Okay, so right sibling of B was C, and it is the right child now of B, so we mark it here. Okay, similarly when we look at C, this is having two subtrees, so left and right, this will be left and this will be right. So always we have also seen that right sibling, it was right sibling of C was D, so here it becomes a right subtree of C becomes D, so you get this. Okay, C and G is connected, and as discussed, G is not having any only one children, so it becomes a left subtree. Similarly, F is there here, F is a right subtree, that's all. So this has one children, but it is a right sibling becomes right subtree. So if it's marked something like this, okay, then it becomes left subtree. So this would be the redesigned structure. So we can look at this structure. This was a tree and this is a binary tree. Why do you call this as a tree? This is called as a tree because each node was having, it was not, there was no conditions, they saying that this has to have two children, so this is having more number of two children, so degree of this node is greater than 2, it is 3. Others are having 2 or 1 or even 0, but it is not at most 2. Okay, it is this one. When you look at most, degree of all the nodes are 2 or lower than that. So that's how we define the left child right sibling. So you can look at one more example, we can work upon this. So you have one more tree given, and what is its equivalent, left sibling right left child right sibling tree, and from this you can get back the binary tree for this. So what is this? A, first level A we have, second level we have B, C, D. So we write B, then the right sibling of B is C, then the right sibling of C is D, so it's connected here. So hope the second level is fine. Third level again, B has the left child, which is E, and E is having a right sibling, so it's connected here, so this structure is complete. Then we look at E is having a left child, and it is the left child is having a right sibling, so this is also connected. So hope this structure is done. Now we are left with this structure and this structure, so we can move on to the second level itself back. The second element we will concentrate, C as one child, so that becomes probably the left subtree in the next stuff, this. Okay, and this is having one right child, which is there, so which means it is having two subtrees, G and D, so this will be a subtree, left subtree, and this will be a right subtree. Finally we are in D now, so D is having 3 children, so we write it as left child H, and I and J are the I is the right sibling of H, and also J is the right sibling of I. So we get this structure. Finally, I and J, they don't have any children, so it's done. Then finally we have M, which is the one child of H, which becomes a left subtree. You can write its equivalent reconstructed binary tree. Okay. Finally, we will stop here. Take this problem statement, get me the left child right sibling representation of this binary tree. That's the problem given. You can work upon this. Okay. Next class we will discuss expression tree. For the time being, hope this much is convenient for you. Problems are given, work on it, and we will look at the other topics in the next class.